How do robots avoid kinematic singularities? Imagine a robot arm trying to reach for something, but suddenly it can't move in certain directions or starts to jerk uncontrollably. That's what happens during a kinematic singularity. These are tricky spots where the robot's Jacobian matrix, which links joint movements to the end effector's motion, loses rank. When that happens, the robot can behave unpredictably, with joint velocities shooting up to infinity or the end effector getting stuck. For electrical engineers working on control systems, avoiding these singularities is a must for smooth, safe robot operation. One way robots steer clear of these trouble spots is by using extra joints, called redundant joints. These extra joints give the robot more options to reach a target without hitting a singularity. When planning movements, the control system calculates the best joint angles that keep the robot away from these problematic positions. It looks at the Jacobian singular values, numbers that tell us how close we are to singularity, and adjusts the joint angles to stay safe. Monitoring the Jacobian during movement is another key. Engineers use algorithms to continuously check the singular values. If one gets close to zero, indicating a potential singularity, the robot's control system tweaks the joint velocities or changes the path. This keeps the robot stable and predictable. For robots with more complex structures, like 7-joint arms, redundancy angles are used. These are internal parameters that help separate the robot's position and orientation control, making it easier to avoid singularities while still reaching the right spot. Path planning also plays a big role. Before the robot even starts moving, its workspace is analyzed to spot regions where singularities might occur. The control system then plans paths that avoid these areas. Sometimes this is done in advance, and other times it's adjusted dynamically during operation. Velocity limiting is another safety measure. When the robot nears a singularity, the control system slows down the joint movements and adds damping to prevent sudden jerks or excessive speeds. Sensors like encoders and for sensors provide real-time feedback. If the robot starts behaving oddly, the control system detects it and adjusts commands instantly. This feedback loop helps the robot recover from or avoid singularities altogether. In practical settings like manufacturing or assembly lines, avoiding singularities ensures the robot moves smoothly and maintains precise tool paths. Electrical engineers design control algorithms that combine kinematic models, sensor data, and real-time Jacobian analysis. This integration helps keep the robot's movements safe, reliable, and predictable. So, in essence, robots avoid kinematic singularities by constantly watching their Jacobian matrices, using extra joints to stay flexible, planning paths carefully, and controlling joint speeds tightly. All these strategies work together to keep robotic systems functioning smoothly and safely in a wide range of tasks.